All right, break time is over. So we're gonna continue with the lecture number 18 when we talk about memory management techniques, because we just learned about the different types of memory. We learned about the internal memory, then we learned about the external memory. Now it's time to take a look on memory management methods. So we're going to talk about the swapping, paging, and virtual memory, VM. Now, effective memory management is very important, especially in multi-programming system. We have some problems which are linked with few processes that are available in the memory. Now, if only few processes are loaded, that means that most of the time they will be in waiting input-output. So during this time, we have the CPU that has to remain in what we call idle, which has to reduce the overall system efficiency as a result. Now, we have this terminology. We have the long-term queue. Here we have, it has to hold the process request, typically stored on a disk. Then we have processes which are brought into the main memory, one at a time when a space is available. Then completed processes, they needed to be removed from the main memory. Now we have the following problem scenario. So sometimes we have none of the processes which is in the main memory are in ready state. That means they are all waiting for the input output. So to avoid the CPU to be in what we call idle state, the operating system, it has to swap one of these processes, then swap it out of the main memory, then keep it in the disk for a while into what we call intermediate queue. So what is the intermediate queue? The intermediate queue has to stall existing processes temporarily kicked out from the main memory. Then the operating system can bring another process from the internal intermediate queue, or it has to honor a new request process from the higher term queue to allow the execution to continue. Here we have this scenario on the screen. We have the long-term queue, which means that we have this job request which enter the long-term queue, and these resources are very limited, and when they are available, that means we have some of the processes which are already done. We need to bring some processes from the long-term queue to the short-term queue, as depicted by this picture. So when they are in the ready state, they need to be executed by the processor, and the processor has to alternate between executing OS instructions as well as the processes. Now, the operating system needed to select which processes are ready, and it has to learn them before giving control of the processor. Now we have this long-term queue which hold job request, and as the resource becomes available, they need to be moved to the short-term queue, and the processor we have to alternate between these processes and the instruction. And you see we have different queues for the input-output as well. So this is the end. Now, what happened? Because we have the processor, the operating system, which needed to bring a process for the intermediate queue or new request from the long-term queue, the new arrived process has to begin its execution. And the execution needed to be continued under the OS control. And here we have, it is an input-output operation. Oh, So this can potentially worsen the computer performance if they do use the swapping many times, because we know that the disk input-output is usually faster than the input-output devices. So the swapping can help to increase the computer performance when it is not overused. But the virtual memory is more advanced, is more sophisticated technique for memory management if you compare with the swapping. Now here we have the scenario of the swapping. Here we have the main system, the main memory, which includes the operating system as well. Then we have the long-term queue, which includes the job request. And you see the processor, we have to bring the processes from the long-term queue into the main memory when the space is available. And those which are completed, they are moved out. Then if there is any space which is available, there will be the processor will get the process from the long-term queue and bring into the main memory. Now, because there might be some processes which are inside the main memory, which are stored into the main memory, and they are not in ready state, that means here it is a problem. The central processing unit will be in what we call idle state. Then to avoid that, we have here the swapping technique. Here you can see we have the long-term queue, we have intermediate queue. Let's suppose the processor has brought a process into the main memory, and the process is not into the ready state, and there is not enough space to store new processes from the long-term queue. Since this process is not in ready state, maybe it's waiting for the input-output devices, so the processor will swap out the process and store it into intermediate queue into the disk storage, then get into a new processor which is into the ready state to avoid the central processing unit to be in idle state. So this is what is depicted by this picture. We have here we have long-term queue, which include different processes, and we have the main memory, and the processes need to be moved from the long-term queue into the main memory, and the completed job needs to be removed from the main memory. Then, since we may have here the main memory which is full because we have many processes, then we need the intermediate queue here, and the processor will use the swapping technique to swap out the processes from the main memory to the intermediate queue of the disk, the storage disk, and get into new processes from the long-term queue, because those processes that need to be swapped out are not in the ready state, to avoid the central processing unit to be into a long idle state. Now, another technique that can be used in memory management is paging. We know that a program runs, so we have many pages. We have a process that can be divided into many pages, and we have a main memory which can be divided into many frames, and a page from the processor needs to be loaded into a specific frame into the main memory. Now we have here the process A. We have a process A which include different pages, page 0, page 1, page 2, page 3, and so on and so forth. This is the process A, which include this page. Then we have the main memory, which include different flames. We have the main memory which include different flames. These are the flames, main memory. Now we have pages from the processor that need to be loaded into the main memory is flame. For example, you can see here we have the main memory and we have the 16 frame and the 17 flame, 19 flame as well, which is in use. That means they are quite busy. Now the next one we have 13 flame, 14 flame, and 15 flame, as well as 18 and 20, which are free. So that means the processor is eligible to load the flames, the page from the processor A into the different flames which are free into the main memory. Now you can see easily that we have the page number 0 from the processor A, which has been loaded into the frame number 18. Now we have here 18, which was free. We have the next one was 15, 17, 16, 15. Then we have 14, which was also free. Then we have 13, which was also free. Now we have the page 0, from the processor A, which is loaded. Now this is the page 0 from the process A. This page 0 needs to be loaded into page number 18. Then here we have page 0, which is loaded into frame number 18, page 0 of A. Then we have the page number 1, which is loaded into the flame of 13, page number 1. These are the frame number. Then we have the page number 2. The page number 2 of the process A is loaded into the frame number 14. We have page 2, which is loaded into the frame number 14 of the main memory. Then we have the next page, page number 3, which is loaded into the frame of 15, page number 3 of A. Then we have the next one is the 16. 16 is in use. In use, that means is busy. This frame is busy. Then we have 17, which is also in use, is busy. Then we have to load the page 0 of A in frame number 18 of the main memory. Then 19 as well is in use. Then 20 is also free. 20 is also free. This is 19. This is 20. Then we have here the page 2, which is loaded into the frame number 14. Then we have page number 3, which is loaded in frame number 15 of the main memory. So this is what we call paging. It has to be done by the operating system. Now, we needed to understand that there is a conversion between the logic and the virtual address. So we need here the logic address. Here, this is the page number. Then we have the relative address within the page. Here is 30. Then we can find easily that this is loaded into the page number 13 as depicted by this picture. Then this is the process of process A. This is the page table of the process A. That means we have a page table for each process. The main memory is divided into frames, as we have seen, equal size frames, and each process is divided into pages. The pages need to be matched to the frames. So we have the pages which are loaded into available frames when a process starts. So a page table, as you can see, is set up to track the mapping between the frame and the page of the processes. Now, this is what we call the page table, which is there to map to store the information about the mapping of the page number and the frame number. Now, what does the system do to do the translation of the process addresses, logic address, and the physical address? We have the process which use the page number plus relative address, as well as the page table to get the physical number. So we have the page number, we have page 0, page 1, 2, 3, and we have the relative address. Then the page need to get the physical addresses using the page number as well as the relative address. So for smaller processes, we have fewer page numbers. Then for larger processes, we have a very big number of pages. So this is very important to note that the page number is related to how big is the process. Now, the next thing that we needed to discuss is the VM. We talked about the paging. Paging enables effective memory management for multi-programming. And we have demanding pages. We have the pages that needed to be mapped to the frames. And we have a page fault when a program accesses a page which is not into the memory, main memory. Then we have fewer pages per processes if a process is smaller, and we have a big number of pages if the process is bigger. So if the operating system found out that there is not enough space into the memory, main memory, that means it has to remove a page and bring a new one. That is what we call page replacement techniques, as we have seen for the cache memory. We have seen that when the cache is full and the system needed to bring a block from the main memory to the cache memory, one of the block into the cache memory needs to be replaced by a new block from the main memory. That's the same scenario for the page number. If the main memory is full and it can't contain any more page from the process, that means one of the page into the main memory needs to be removed using what we call the page replacement policy. Then we get into a new page into the main memory. Now, there is excessive page swapping. So if a page has been removed and the operating system is looking again for the page into the main memory, so this is called the trashing. So it's going to slow the execution. Now here is the page structure. The page page structure, page table structure. As we have seen, it has to include the page numbers to allow the translation from the logic addresses to the physical address. Then we have the memory access, which requires translation of a virtual address to the physical memory. Then a virtual address consists of a page number as well as offset. Then we have a physical address, which consists of a flame number as well as an offset. The translation needs to be performed. Then here we have the page number, and we have the main memory, which include the flames. We have the page from the processes that need to be loaded into the main memory. For example, this is the VAX process, which can contain up to 2 gigabytes. That is 2 gigabytes. 2 gigabytes means we have how many bytes? 2 gigabytes, that is 2 gigabytes. We have 2 to the power of 30. Then we have 2 to the power of 31 bytes. Byte of, this is a VM. Then we have also the page size, which is a 512 byte. So for a page size equals to 512 byte, that is 2 to the power of 9, page size. Then we have page size equals to 512 byte, that is 2 to the power of 9 byte. Then we can easily find the page tables entries. The page tables entry is equals to number of page entries, page table entries, page tables entries is equals to 2 to the power of 31 divided by 2 to the power of 9, and this is 2 to the power of 22. 2 to the power of 22. We have page entry table, page tables entries. So given the virtual memory size and the page table size, you can easily find out the page table entries. So this is for EVX. Now we needed to invert the page because, as you have seen, for each process we have a page table. So for a big number of processes, that means we have a big number of page tables. So we needed to use inverted page table structure to allow the system to use a virtual page number, which can be mapped to a hash value. Then the hash value needed to point to the table with one entry per a Lily memory frame. We have also to handle the co-regions using the hash value, or we can also use the chains, usually with 1 or 2 entries. So we call it inverted page table because the entries are indexed by frame number rather than page number. Here we have the inverted table structure. We have the page number. We have, for example, n page number. N bit for the page number. Then we have the offset. Then we have here the hash function. So if we take the n bit and we apply the hash function, we get m bit, and we have the inverted page table, which include the processor ID as well as the page number. And here we have the chain, and the chain here is being used to allow to handle the co-regions. So that's why here you see that we have the inverted page number, which is a 1 entry for each physical memory frame. Now, translation look aside buffer. We need every memory, virtual memory reference to require at least two physical memory access. One is for the page table entry, another one is for the data. So this will double the memory access time in straightforward virtual memory scheme. So most of the virtual memory system, they use a special cache for the page table entries that we call the table look aside buffer. The table look aside buffer is like a memory cache, and it has to store recently used page table entries. So we have seen the memory cache. So the table look aside buffer is like the memory cache, which stores the most recently data. For the table look aside the buffer, it has to store the most recently used page table entries. Now, here we have the operation of the paging and the table look aside buffer. It has to start, and the CPU needed to check the table look aside buffer, and if the page table entry is in the table look buffer, then it will be returned to the central processing unit, and the physical address will be generated. Now, if the page table is not available into the TLB, that means the system needs to get access to the page table, and if the page is not in the main memory, it is a page fault. If the page is available in the main memory, that means that the TLB, the table look aside buffer, needs to be updated. Then we need the central processing unit to generate the physical memory. Now, what happened for the page fault? If the page is not available in the main memory, we call it page fault. Then the operating system needed to instruct the central processing unit to read the page from the disk because it's not available into the cache, into the main memory. Then the central processing unit has to activate the input-output hardware. Then it has to get the page that needs to be transferred from the disk to the main memory. So this is the same process for the cache memory. If the block is not available into the cache memory, that means the system we expand is requested to the main memory, then the block will be transferred from the main memory to the cache memory. So for the page fault. What is the problem? Clear? So we have the page fault. That means the page is not available into main memory. The central processing unit needs to go through the disk and found the page into the disk. Then it will be loaded from the disk into the memory. What is the problem today? Hello? What is the problem? It's very hot. Take a piece of paper. Please take a piece of paper. Okay, it's fine. You can use mine. Only use this paper. Only use this paper, okay? don't do it, I will call you to come to my office to do it in front of me. I'm giving you the time to do it right now. Done? If you didn't receive your email, write down your student ID in our course WeChat group. You don't write down your email, your student ID in the course WeChat group. Then I will send you again the email. Okay? If you haven't received the email, write down your student ID in our course WeChat group. Your email, then write down your student ID in WeChat group. I will send you. Which class?
Technical report, right?
This is for microprocessor.
I know, but it is a whole together, a whole class together, all class. Yes, one.
Is all at once?
Yes, one. You go ask students to click all the teachers to sort them, and it should be solved at one.
That is how it's a concept. You all down? For which course? All the courses? How it comes? How can you evaluate all the courses at one time? All the teachers. So if I am bad and there is another teacher who is really good, how do you evaluate?
The first one teacher and the next one.
Write down the name of the teacher, no? The name of the course. So how many teachers? You have more than one. So how do you select? One by one? You choose one out of four. Three out of four.
I did not get the email before.
Okay,
I'm
I'll
from
send you
the
the
21 and they are 23.
Okay, I'll send you the email. Write down your student ID. So everybody has done it, right? Because I'm going to check it. Everybody has done it. Except 21. Hello, make sure you do it. This is the time to do it. If you know you haven't done the course evaluation, this is the time. Okay? This is the time to do it. Have you done it? Show me. Done it here? So this is very important for us. Please make sure you do it. For my classes, I do make sure that everybody has done it. So if I found out one of you hasn't done it, I will have to call you and come and see me. Please make sure you do it right now. It is very important for us. We need to keep improving the course materials, the teaching style, and many others. So it is very important that all of you try to do it. Clear? Finish?
I did not receive the email.
Write down your student ID in the course WeChat group, then I'll send you the email again. If you haven't received the email for the course evaluation, please write down your student ID in the course WeChat group, then I will try to send again the email. Okay, that's it for today's class. I'll see you next time.